Welcome back to the home lab on what is a pretty wet and cold wintry day. In fact, I've lit the fire to try and keep myself warm. So what I'm going to show you today is an interesting and quite retro display technology, and I'm going to build a project to explain how it works. So what we're going to look at is vacuum fluorescent displays. So, as I'm sure you already know, I'm quite a fan of retro display technologies, and you might have seen the video I did on building this little Nixie tube display, which uses a gas that glows, or this one, the Pneumatron, which actually uses hot filaments, and those hot filaments, when lit up, show you the letters. But today I'd like to look at something slightly different. What I'd like to show you is the vacuum fluorescent display that works in a different way from these two. It actually uses a fluorescent screen, and I'm going to build this project and then demonstrate how the tubes actually work inside. As I've probably said before, you can have all the gear and electronics kit to play with, but if you haven't got a project, it's not much use. So I thought I'd explore these vacuum fluorescent displays, but rather than just show you one working on the bench, you need a project, as I said. So I thought the project we build is a little display that displays the number of the video you're watching. So you're currently watching video number 203. So let's look at how these work and how I built this display. Just before we start, again, a huge thank you to all of you for watching, and to some of you who decided to subscribe to this channel, which is lovely. I also really appreciate the comments you make. I am again really grateful to PCBWay, who always encourage me to make videos and let me kind of do my own thing, which I'm doing here. But as you know, they make bespoke printed circuit boards, and they would be particularly suitable for a project like this because a lot of people use these kind of displays to make clocks. So why not head over to their website and have a look, and I'm sure you might get some ideas for the project that you'd like to do. So vacuum fluorescent displays, or VFDs as most people call them, were pretty ubiquitous displays until fairly recently. You'd see them all over the place. Car radios with all sorts of different colours and things. There's some on the CD player I've got, and they were very popular for calculator displays. They have the advantage of being like really, really bright. They've got a really good viewing angle. I can read this even from over here. They work in an absolutely huge range of temperatures. And whilst these are 7-segment displays with a decimal point, how you set up the anodes gives you the arrangement that you can have for letters. So with different shaped anodes, there's really a limitless arrangement of displays that you can have. And they made for a very, very good and very reliable low power display. So let's have a closer look at how these things work. So let's now have a look at the project I wanted to build. So the first thing I had to do was order 10 of these IV22 VFDs and the associated sockets, which are PL31A-P, and they came from the Ukraine for about £50, including the postage. There's lots of old Russian and Ukrainian stock that remains, as they use these devices well into the, I think, 1990s, when in the UK the larger VFDs were becoming a little bit obsolescent. Now, with old stock like this, you might well wonder where these tubes have come from and what they were used for, because these were second-hand ones, not new old stock. So for the more paranoid amongst you, knowing these tubes came from the former Soviet Union, you might be concerned that they're contaminated and perhaps radioactive. So to put your mind at rest, I ran my Geiger counter over a radium dial first to check its operation, and then over the box. Well, as you might guess, all was well, though the more observant of you might point out that this didn't really test the tubes for alpha radiation. Anyway, I digress. So let's get on with the project. So I've got a couple of pictures here to show you how the VFDs work inside. So here's one that's in the form of a glass tube, and you can see the getter here, the black, which means that it's been evacuated. And you can sort of think of it as a sort of mini cathode ray tube. So you've got the glass front, then behind that you've got a filament, then behind that you've got a grid, and then behind that some anodes, and the anodes are coated in a material that will fluoresce when electrons hit it. So it's a kind of triode. Now it's a bit difficult to see in these pictures, but here's the front of the tube, and you can see just here maybe and just here the filament wires. Now they have a low voltage and a low current, about 1 volt, so you don't see them glowing, they don't get red hot, but they're covered in a material that has a low work function, so even at the temperature they're at, they can give off electrons easily. Now, beneath that is a grid. You can probably see this crisscross pattern here, and that's made positive, so that will accelerate the electrons from these filaments towards the back of the tube. Once it hits the anodes, which are also positive and usually at the same potential as the grid, they'll hit the fluorescent material on here, and you can use different colours, and they'll lose their energy and release it as a photon of light. So you'll see a segment glowing if the filaments are on, the grid is positive, and the most important thing, the anode itself is positive. So here you can see the whole tube is on, but the remaining segments aren't made positive. Those anodes are grounded, so they don't switch on. Now, the only problem I had is I want the word video for video number whatever, and you can only get a V, that sort of shape, with a 16 segment display. But I hope you'll let me get away with using a sort of U shape with the 7 segment displays that I've got here. Now, when you see things that look like thermionic valves and these behave in a very similar way, or a cathode ray tube, it's sort of cathode ray tube in reverse if you think about it, the screen's at the back rather than the front, you think high voltages, but in fact they're really easy to get lit up. You need about 1 to 1.5 volts on the filament, and about 20 or thereabouts volts on the grid, and exactly the same voltage on the anode that you want to light up, and it then lights up perfectly. So the next thing I did before starting my project is just check the wiring on the base of these to work out which pin was which. And if you're familiar with 7 segment displays, it's really easy. In the UK, it goes A, B, C, D, E, F, G. And I thought, right, let's get wiring. I thought, no, I better have a look at the data sheet. And these are really odd. They have a different way of labelling the letters. So you'll notice it goes A, B, C, D, E, F, G. So other than looking at the data sheet to get the voltages I needed to use, it was important that if you build something like this, you look at the pinouts, because pin D on this type of Russian VFD is not the same as pin D on a normal LED 7-segment display. So, as I've said before, it's all right having all these bits and pieces and loads of components, but you need a project. So what was I going to do with these lovely VFD tubes? Well, having already built the FJ physics display out of Pneumatrons, I thought it might be fun to build a display which showed the number of the video. This one, as you can see, being video number 203. So, to begin the build process, I drew out a load of 7-segment display shapes and began the process of deciding what the layout of the VFD tubes would be and how I would write the text that I needed them to display. The first electrical thing I had to do was desolder the wires that were still attached to the used tube bases. Interesting to note that under the sleeving, some of the joints were of a really poor quality. This took quite a while, but with all the bases cleared of their old wiring, it was time to work on the final layout of the tubes. As you know, I really like these hexagonal brass spacer standoff pillars, and I think they look great as part of a project. And because they're a fixed length, they're quite easy to use. I've got a box of these, they're quite cheap, so I selected suitable ones to mount the tube bases and screwed these onto the now wire-free sockets. It was now time to think of the kind of base I would need to mount them on. As ever, I decided to go to Perspex to build the base for this, and I bought a sheet of A3 clear blue 3mm Perspex. And once this arrived, I drew out where the tube bases might go, remembering the spaces that were needed between the words. This wasn't an easy task, and once I completed it, I changed my mind to make the whole thing less wide, with 2 rows rather than one of text, because my Numatron one was 1 row, if you remember. With lots of minor changes, this took ages to get right, making sure I had it correctly centred, and that I'd left enough perspex below to later mount the other bits of electronics like the power supply that was needed, and the plug board that was going to be used to set the characters to display on each tube. Now, I'm not sure if you're familiar with Proxon tools. They're a bit like the Dremel ones, but they're absolutely fantastic. So with the perspex marked out, I used my Proxon drill and stand to drill all the holes needed to mount all of the tube bases, hopefully getting them in the right place the first time. Then outside to a rather cool and autumnal garden to cut the perspex sheet to size on my trusty desktop bandsaw, followed by application of a heat gun to bend the display frontage to shape. Probably not the best way to do this, but it seems to work for me. It was then back to the electronics bench to begin the lengthy task of wiring up all those bases. I began by connecting all the filament heaters in parallel and then moved on to the grids. All of the anodes of the letters, as well as the hundreds digit, could be hardwired as these weren't changing. With bits of the wiring done, I tested the sections I completed, usually finding errors or poor joints. With this done, I could now screw the tube bases onto the perspex stand and get a feel for what the final item was going to look like, with the tubes mounted in their sockets. I was a little bit distracted as whilst putting it all together, a telegraph pole was being wielded by crane right outside my window. It was also a good time to play with the filament voltage and current, as well as the anode grid voltage, to see how these affected the brightness of the tubes. Wired as they were, a filament voltage of about 1.5 volts at half an amp for the whole lot seemed to work well, with a grid anode voltage of about 20 to 25 volts, of course at a much lower current of about 10 milliamps. Now, you may have noticed that the last 2 numbers, however, are going to change quite frequently. I mean, I don't think I'm going to be at 300 or 400 videos soon. So I decided to connect the segment's anodes to flying leads with 2mm plugs so that the arrangement of lit up segments could be individually selected, changing the displayed number. I drew out a grid of all the different segments that could be on or off to see what layout of plug sockets I needed. You'll note the number 1 has the smallest number of lit segments at 2 in total, with 5 off, and the number 8 obviously has all 7 segments lit up. So I went for a grid of 7 positive 2mm sockets and 5 grounded sockets for my number change plug board. With this wired up, I gave it a brief test to see that it all worked as expected, and then gave some thought to how I'd label each flying lead and perhaps provide a key with the segment locations, as they're not lettered in the same way as ordinary and regular 7-segment displays, and I'm absolutely bound to forget that and plug in the wrong plugs to get my displays lit up and then wonder why it's all wrong. If I do ever reach 300 videos, I'll have to make some changes to the hardwired hundreds digit, of course, but it'll only involve actually reversing connections to the E and F anodes. As an aside, it's taken me about 30 years to find a use for these RS Components 2mm plug sockets, with a memorable stock code of 444444. So, at last, they've been used. Now, if you're anything like me, you'll know I have a real problem providing power supplies for my little projects, and I particularly don't like things that involve lots of batteries that are going to run out or need to be recharged, or things plugged into the mains because it doesn't make them very portable. But in the end with this one, I had to sort of find a middle ground. So I used one of these adapters, we call them. It's not really an adapter, is it? Mains power supplies that I found lying around, and it gives me 12 volts at about 2 or 3 amps, so that's plenty for this project. And here it is. So the mains coming in and the 12 volt DC supply. That then feeds to a switch to switch it on and off, and a current limiting resistor and an LED to show the power supply is on. And then you can buy very cheaply these little boards. This one is an MT3608, which is a boost converter. So that will take a voltage in and boost it up. And I've adjusted it to about 25 volts to feed to the anodes and the grids of the project. And the negative rail is commoned right the way across. The 12 volts also goes to a buck converter, an LM2596. That was also adjustable, and that one allows me to reduce the input voltage down to about 1.5 volts, and that goes to all the filaments in parallel. And that worked as a really good solution to the power supply problem. Let's have a look at the circuit diagram so you can see how I've wired these tubes up. So it's really very simple, and that's the joy of these things. So if you remember, here's the tube that I've drawn in a slightly different layout, and you can see the pin numbers that go to the filament. The hot filament boils off the electrons. If you remember, they're accelerated to the positive grid here, and then they continue across to the anodes, and each anode has a number on it so you know which segment you're lighting up. So on the other side, here's my low voltage supply. Obviously I don't use a battery, but I'm indicating it as such, and all the filaments are wired up in parallel, and I've actually got just over 1.5 volts, but you've got to be careful you don't burn them out. And then the higher voltage power supply, again, not a battery, but you've seen what I've done on my power board, 25 volts going directly to the grid and also to all the anodes that I wanted lit up. Now, if you remember, most of the tubes are hardwired, so I've come straight to each anode and wired up positive to the ones that I want on, and I've grounded the ones I don't want on. But the last two, where I'm going to change the numbers, I've got flying leads, so the flying leads will either connect down to ground and they'll be off, or to the positive and they'll be on. Now I've kind of drawn the flying leads the other direction here, but in fact they come off each anode and they either go to the positive or they go down to somewhere that's grounded. But you can see just how simple these things are, how easy they are to wire up, and in fact the voltages they're using and the currents are very low, so they're actually very safe. Oh, being a physicist, I just can't resist but add this little bit. If you remember, I said these are a little bit like a cathode ray tube in reverse, in that they've got the heater at the front, then the grid, and the display at the back, not the front of the tube. And you might wonder why you can get away with such small voltages. Well, the heater isn't a problem, because they can be quite low voltages normally. But how can you get away with 25 volts to accelerate the electrons? Well, the way that happens is that the distances in here are very, very small, and the filament might be about 2 millimeters in front of the grid. So if it's 2 millimeters in front of the grid and the grid's at 25 volts, then we've got a potential difference between the two, and we've got an electric field of about 125 volts per centimetre. Now, if you think about that in meters, that is 12,500 volts per metre. So that's plenty of electric field strength to accelerate the electrons across the tube and crash them into the anodes with their fluorescent coating. You might have noticed on the earlier bits of the video that when I had these tubes wired up to the power supply on the bench, some of the segments weren't lit up very well. I think they're quite old tubes. They've been used in other devices before I bought them. But it's interesting, since I made my own power supply, they seem to be lighting up really well. And in fact, I'm using exactly the same voltages. I might change these tubes for some new old stock that haven't been used before and try and find out, I don't know if you can see it on the camera, what's going on with that one. It's all rather strange. Anyway, it's been a fun project and I've enjoyed building it. So I do hope you enjoyed that video and you feel you've got a better understanding now for how vacuum fluorescent displays work, and you'll probably begin to see them all around you, especially on slightly older items of electrical equipment. I'll have to rewire this one now for video 204, and hopefully I'll make that fairly soon. Do stay to the end of the video, because as you know, I often cut in bits after I've finished that I haven't used in the main body of the video. And leave a comment if you enjoyed it or you've got something to add. I'm always interested to read them. Anyway, time for me to set this to video 204, get making another video, and I hope to see you then.